about volumes, and what's the focus mostly is on solids of revolution, what we call solids of revolution. We'll get to that in a bit. But the idea is, so here, the idea is you have some kind of a solid, maybe like this way, maybe it's like that. And so the idea is, well, there's this one, wait a minute. I should have done that one over here. Oops. Let me draw something different here. Okay, so the idea here is you got a solid like this. And what happens is you set this up like you set an integral up like this. Say from A to B. And you take these cross-sectionals. You take like a cross-section at each, you make a slice this way, you take a cross-section, and you calculate the area there. Okay, so the cross-sections will be cross-sections. And you integrate from A to B, and that gives you the volume. If you integrate this cross-sectional area from A to B, then that gives you the volume. Now, if it's like this one, then you set it up like this, where you're going from C to D, and you're taking cross-sectional areas this way, okay? So those are the two main ones that we're talking about. Okay, so let's go ahead and then yeah, so basically this right here, this is a cross-sectional area that you're integrating across over. Now this varies as you go from C to D, but that's fine. You just take, as long as you can find a formula for it, it depends only on Y. For this cross-sectional area, then we're good. And also the same thing, as long as you can find a formula here for it, and in terms of X, A of X, then you're good. You can integrate that. And as long as you know it's something you can integrate. Now, if we were trying to, like if you had something like this, an object like this, and you try to integrate in the Y direction, then your cross-sections are going to look really weird, and maybe that'd be impossible to find a formula for it. Likewise, if you try to integrate something like this in the X direction, then the cross-sections are going to be really weird. Okay, so you try to look for which way it's going to be easiest to find these cross-sectional areas. So now we get to some examples. Number 1, find the volume V of the solid obtained by rotating the region bounded by the curves y equals the square root of x minus 1, y equals 0, and x equals 4 about the x-axis. Sketch the region and then sketch the solid in the typical dish or washer. Okay, so this is the one, this is going to be the answer right here. This curve on top is y equals the square root of x minus 1. Y equals 0 is this curve on the bottom, it's the x-axis, and then x equals 4 is this vertical line right here. Okay, and so you can see that this is the area that this is the region that they're talking about. They don't want you to find the area of this region, but rather, basically what's happening is they're going to rotate the region about the x-axis. Okay, so it's rotating about the x-axis. That means it's going to be rotated this way about the x-axis. So they're just going to take that and rotate it around. Okay, now, I think they've done a really good job of this on the homework. So let me flip over to helping you visualize this. So let me flip over to the homework really quickly. Okay, so you guys can see the homework screen, right? Okay, so there's the answer right there, the first part right there. Okay, now if you scroll down to the second part, okay, so imagine this region being rotated around the x-axis, and it's this one right here, and you can actually see it rotating around. Okay, so this right here is this top curve is y equals the square root of x minus 1, and then this is x equals 4 over here, and then it's rotating about the x-axis like that. Okay, and then they have other options, but this is the answer right here. These other ones are different curves that are rotating about the x-axis. Okay, so that's kind of interesting. I guess it does that. Oh, okay, there we go. So this is going to be the answer right here. This one right here. So let's go back and calculate that area. And the main thing is, let's not color. Okay, so the main thing, so what's going to happen is as you rotate this around, you're going to like get, like if you look at it from this side, it's going to look like an object like this. Okay, but it's going to be, but it's all solid. Okay, so what happens if you take a cross section of that? And what color can I use? Okay, let's say you take a cross section of that. You take that cross section, you're going to get a circle. Okay, is what you're going to get. And the radius of that circle is going to be this distance from here to here, which is going to be the square root of x minus 1. Okay, the area of that circle, the area of this circle that's the cross-sectional area, is going to be pi r squared. Okay, so it's important to identify. Don't just you could just like say, oh, there's that function right there. Let's identify that as the radius every time. But then you'd get messed up if you do that, by the way. You have to look at the situation and look at the graph and figure out what the radius is, because sometimes the radius is not going to be just, take this right here and make that the radius. Okay, so anyways, the cross-sectional area is pi r squared, which we plug in this value r here, and you just get pi times x minus 1. Okay, so now the volume from the first page, the integral was a to b of a of x dx. That's the formula from the first page. And you can see that you're going to get right from 1. So a is 1 and b is 4. So you're going to go from 1 to 4. Here's the area, pi x minus pi. We'll write that like that, dx. Okay, so that just goes into there. Okay, so now you integrate this. This is pi x squared over 2 minus pi x. Integral that's that. Integral pi, if negative pi is negative pi x. And then that goes from 1 to 4. Put in the top limit first. Subtract and put in the bottom limit. So let's see, that's going to be 16 pi over 2 minus, this is 4 pi, so that's going to be 8 pi over 2. Okay, now distributing this in, that's minus pi over 2, and then minus, that's plus 2 pi over 2. Let's see, 16, 8, 9 pi over 2. Okay, so 9 pi over 2 is going to be the answer. So great. Let's go to the next one, number 2. If you have any questions, just speak up, by the way. Okay, so you want the region bounded by these curves, y equals x cubed and y equals x, and x greater than or equal to 0. Okay, so y equals x cubed, that looks like this, and y equals x, that looks like this. And they intersect here and here, which is important to know. And you'll only want to know where x is greater than or equal to 0, because it does come down here, and they do form a little region down here as well, but that's when x is less than 0, so that's excluded. Okay, and that's going to be revolved about the x-axis. So here's the x-axis. So that's going to be revolved this way again. Okay, so what's going to happen is this line right here revolves to here, and then this curve, y equals x squared, it revolves to here. Okay, so you're going to get this right here. And yeah, let me just go over. So this will be the answer right here, by the way. This one's the answer, because here this has the same curves, but it's doing this wrong region here, and this one's not even y equals x cubed, and that's not even y equals x cubed. It looks more, maybe it's the y equals the cube root of x. Okay. Let's see here. We can look at, so I determined it's this one right here being revolved around. So that is going to be not that one. What the heck? This one here. Okay, this one right here. You can kind of see the line on the top, and then the y equals x cubed underneath it that's rotating around. And it's kind of hollow in the middle, by the way. It's got this big hollow part in the middle. Okay, so let's go back to the drawing here. So that's being revolved around like that. And if you take a cross-sectional area, it's best to cut it this way, perpendicular to where it's rotating. Cut it this way. When you cut it that way, what you're going to get is you're going to get a washer. Okay, because the middle part is empty, so that's empty. So it's just this, or maybe that's like, whoa, that looks like a donut. Whoa, donut. This is tasty, tasty math. Okay, so anyways, you cut it this way, you take a slice that way, you get a washer. Okay, now the area is going to be pi times the outer radius squared minus the inner radius squared. Okay, the outer radius goes from here to there. That's the radius. Just half of, just like from the middle to the top. The outer radius is x. Okay, if that's x, that's x, because y equals x. And then this is y equals x cubed. So the inner radius is x cubed. Okay. Now these intersect at the point 1, 1. So when we set the integral up, okay, volume is the integral from a to b of pi r squared minus r squared, little big R squared minus little r squared dx. Your a is going to be 0, and your b is going to be 1. So you're going to go from 0 to 1. Big R is this one. Little r is x cubed. Okay, so 0 to 1 of pi x squared minus pi x to the 6th. Okay, integrating that one, you get pi x cubed over 3, and this one is pi x to the 7th over 7. going from 0 to 1. So that putting 1 in, we get pi over 3 minus pi over 7. Putting a 0 in, you just get 0. Okay, putting 0 here, that makes that all 0. That makes it all 0. So that's 0. So pi over 3 minus pi over 7. And I guess you could get a common denominator. So that's 7 pi minus 3 pi over 21. 3 times 7 is 21. So 4 pi over 21 would be the answer. Okay, great. So let's move on to the next one. Number 3. Find the volume V of the solid obtained by rotating the region bounded by the curves. Okay, so you have y equals 3 sine x, y equals 3 cosine x, and from 0 to pi over 4, and you want to rotate it about the line y equals -1. So you're rotating about this line down here, y equals -1. You're not rotating about the x-axis, it's rotated about that line down here. Okay, so sine x starts at the origin and goes up, right? So that could be 3 sine x. This might be able to be y equals 3 sine x. None of those can be, so throw those out. And then cosine x starts up here at 3 and comes down. So that could be 3 cosine x. That can't, none of these could be it. So this has got to be it right here. Okay, so here's y equals 3 cosine x up on top. On the bottom is y equals 3 sine x. And you're rotating about this line down here. Okay. Let's take a quick look at Webassign. No, that's not it. This looks like it right here. That top one is y equals 3 cosine x. That's one that's going to the top, that blue one. And then the one that's going through this, that's tracing out this little cone in the middle, is y equals 3 sine x. Wait a minute. Yeah, because it's rotating about this. It's rotating about this line y equals -1 down here. Okay, so it's completely hollow in the middle. That one, no. That one, no. That one, this one's rotate. Wait. No. Okay, it's got to be this one right here. Okay, so let's go back. And the thing is, it's rotating about this right here. Okay, so the image will be something like this. Dang. The image will be something like that. Dang. Oh, it's just supposed to be the image of this piece right here. This is supposed to be an image of that piece right there. I really badly drawn. Okay, something like that. Okay, so it's supposed to be that, an image of that right there. Wait, it's probably down to here actually. Okay, so when you take a cross-sectional area, slice it like that, then what you're going to get is a big washer, like that, a big washer. And here, the outer radius goes from here to here, okay? So the outer radius is going to go all that distance. Now, from here to here, it's 3 cosine x. But you've got an extra 1 there. So it's going to be 3 cosine x plus 1 will be the outer radius. Okay, the inner radius is going to go from here to here. From here to here. So that's 1 there, and this one is 3 sine x. So that's 3 sine x plus 1. And your area of x is going to be pi times r squared minus little r squared. Okay, in fact, we can go ahead and do that one. So that's going to be 3 cosine x plus 1, because that's what big R is, squared, plus minus 3 sine x plus 1 squared. So if you expand this out, you get 9 cosine squared x, and then the middle ones is going to give you 6 cosine x, and then the last one is going to be plus 1. And then you're going to get subtract the square of that, so that's 9 sine squared x minus 6 sine x minus 1 is what you get there. And the ones are going to cancel. This and this one combine. There's a trigonometric formula. Or a trig identity. That cosine of 2x is equal to cosine squared x minus sine squared x. Okay. So that means that this minus that is 9 cosine 2x. Okay, so great, we get all that stuff. We got all that good stuff there, and that's our area, A of x. So the volume it's best to integrate this way. So these intersect when at power of 4. Okay, so you're integrate from, so that's what our b is going to be. Our a is going to be 0, so we're going to integrate from 0 to power of 4. And we're going to integrate all this. So this is, I'll pull the pi all the way out, and so we have 9 cosine 2x plus 6 cosine x minus 6 sine x. Okay, so I integrate this. This is going to be sine 2x. If you take the derivative of sine, you get cosine 2x times 2. So we'll just divide by 2. And that means that this will handle the 2 that comes out, and then we have 9 cosine 2x. And then here you have 6 sine x. Derivative of sine is cosine. The derivative of cosine is negative sine, so that's actually plus cosine x. And this is evaluated from 0 to power of 4. Okay, so upper limit would be 9 sine. Okay, plugging a power of 4 in here gives you power of 2. Plus 6 sine power of 4 plus 6 cosine of power of 4. Now subtract, put zeros in and subtract, so that's 9 sine of 0 plus 6 sine 0 plus 6 cosine 0. Okay. Sine of power of 2 is 1, so that's going to be 9 halves. Sine of power of 4 is root 2 over 2. Cosine of power of 4 is also root 2 over 2. Sine of 0, sine of, and these are both going to be 0. And cosine 0 is 1, so that's going to be, but it's minus 6. Let's see, 6 is also 12 halves. So you have 9 halves minus 12 halves. And then these two combined together, this, you've got these, so 6 over 2, that's 3. 3 root 2 plus 3 root 2, that's 6 root 2. And then 9 halves minus 12 halves, that's 3 halves. Okay, so that should work out as the answer. Any concerns about that? Okay, let's go on to number 4. Okay, find the volume V of the solid obtained by rotating the region bounded by these curves, y equals 8x cubed, y equals 0, and x equals 1. We're going to, about the line x equals 2. Okay, so here they have the line x equals 2 here, 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 and here. Y equals 8x cubed, that looks like this right here, that curve right here. None of the other ones look like that, so this must be it right here. Y equals 0, that's the bottom right here. And x equals 1 is this right here. And you're going to rotate it about that curve there. Whoa, this is weird. Everything went away. Okay, so y equals, what the heck? 8x cubed. This is x equals 1. And this is y equals 0. Oh, dang. Oops. Okay, so everything is written there twice, I guess. Yeah, that's messed up. I can't erase it. Ah, so annoying. Let's see here. Okay, so let's move on. Okay, so this curve is y equals 8x cubed. This is x equals 1. This is y equals 0. Okay. So those are the boundaries. This is the region, and it's being rotated about this line x equals 2 right here. Okay, so let's hop over to Webassign, and we'll take a look at what's going on there. Okay, so here we have this as the answer to the first part, and that's being rotated this way. That's going this. That's going to be going this way. It's going to rotate that way. Okay. This is the one right here. This is the one. It's rotating about there. Okay, so here, so let's go back to the other document. So here, what you want to do, so it's going to rotate this way, and you're going to get, you're going to get a reflection over here. Okay, so you get this reflection right there. And you want to take cross-section this way. Okay, so, and that's going to give you a washer again. Okay, so you have to figure out what's the outer radius of that washer and what's the inner radius. Okay, so the outer radius is going from here to here. And it depends on your value of y, actually. Okay, so what you want to do is you want to take this equation right here, and you want to solve for x. Okay, so if you switch and do it the other, so basically what we're going to do is we're going to be integrating from 0 up to 8. We're going to get from 0 to 8, and you want to integrate. So here's the deal. We're using this formula here. Okay, because it's easier to find the cross sections this way than it would be to find cross sections this way. Okay, so we're integrating this way because we can slice this way. We can find the cross section. It's a nice washer. Area is pi times the outer radius squared minus pi times the inner radius squared. Okay, that's what that is. Okay, so the outer radius, though, it has to be in terms of y. You can't have it in terms of x. So what you need to do is take this and solve for x. Okay, so so you have x cubed equals y over 8. And that's taking this 8 over to the side, so x cubed is y over 8. Then take the cube root of both sides, and you get y to the 1/3 over 2. Cube root of 8 is 2, so you get that. Okay, so this curve here is also known as x equals y to the 1/3 minus 2. That's what x is. Okay, so this distance from here to here is x, or this distance from here to here, it's y to the 1/3 over 2. From here to here, it's 2. This distance is 2. Okay, all the way from there to there is 2. So from here to here would be 2 minus this. It's 2 minus y to the 1/3 over 2. That's the big radius from here to here. Okay, so it's, all this distance is this again. This long distance is 2. From here to here is 2, because that's 2. That's 0. From here to here will be 2 minus this distance. This distance is y to the 1/3 over 2. Okay. Inner radius is easier. That's just 1. Okay, so r equals 1. That just goes from here to here. That's just 1. Okay, so I'll go ahead and write down our volume. We're going to go from 0 to 8 pi outer radius squared minus inner radius squared dy. Okay, so that's our area there. It's pi times the outer radius squared minus inner radius squared. Okay, so let's go ahead and square all that out. That's 4 minus, okay, multiply those together, you get negative y to the 1/3, double that, so minus 2y to the 1/3. And then square this last one, that's going to give you y to the 2/3 over 4. And then this is minus 1. And 4 minus one is 3, so I'll just change that to a 3. Okay, now I'll come down here, and we'll go ahead and take the integral. Integrating 3, you get 3y. Integrating this one, it's going to be, let's see, 1/3 plus 1 is 4/3. Okay, so when you take the derivative, you'll get, you get a 4/3 coming out, so you need a 3 up here to cancel that, but you have a 2 there, so 3/2, that'll do it. Okay. So now, when you take the derivative here, you have a 4/3 coming down. This 2 will reduce the 4 to a 2, and this 3 will cancel that 3 out, and then you'll have this minus sign there, so that's fine. This one, okay, so you have 5/3. So you need 3/5 to get rid of that, so we'll put a 3 there, and we'll put a 20 there. So 5 times 4 is 20. So now when the 5/3 comes down, this 5 will reduce that to a 4, and the 3 will cancel that 3 out, so you'll just get that. Okay, and now it's going from 0 to 8. Okay, now I'll plug the 8 in first, so that's 3 times 8 minus 3 times, okay, y to the 4/3 is 8 to the 4/3, which you take the cube root first, that's going to be 2, so 2 to the 4th. And then here, this will be 3 times 2 to the 5th over 20. Okay. This is 24. This one will be, this 2 reduced that to a 3, so 3 times 8, that's 24. That's also going to be 24, or minus 24. And then we have plus, what is that? 3. Okay, so 2 of those will come out. So that's 3 times 2 cubed. That's 3 times 8 is 24 over 5. And then these are going to cancel, so you get 24 pi over 5. Okay, so good. That's number 4. Okay, so it's important not just to take the area, not just take the radius to be this one, because you're gonna get it wrong. You have to look at the you have to draw a picture, look at it, figure out what radius, take the distance from the axis of rotation to the point that you're after. Take that distance, and that's your radius. Or one of your radiuses, or maybe there's another radius. Okay, so let's look at number 5. So number 5 is find the volume view of the frustum of a pyramid. So it's the portion of a pyramid that remains after the top part has been cut off by a plane parallel to the base. Okay, so the square base has, this side is length B, the top is length A. The top side of left side A, and height is H. Okay, now, so what you want to do here is you want to take cross-sectional areas as you're going up the frustum from the base. So maybe you think of it this way. Going from 0 to H on it, and you want to integrate the cross-sectional area as you go from 0 to H. Okay. Now, here's what I'm going to do. This goes up linearly, or the length of a side acts linearly as we go up in Y, as we increase in Y. Okay, so let's do this. Let's let S of Y equal the length of a side at height y. Okay, so we know that when, so if we set it this way. So think of it this way. So think of y as being your independent variable and L or length as being a dependent variable. Think of it that way. So when y is 0, the length is b. And when y is h, the length is a. The length is a. Okay. So what I'm going to do is I'm going to calculate the slope of this line segment, of the line segment that joins these 2 points. So it would be a minus b over h minus 0. Okay, and so to speak, like if this was x and y, then b would be the y-intercept. So you can do this way. So s of y is equal to the slope times y plus b. So b is the y-intercept. In this case, it's a different intercept because this. Okay, so that's what s of y is. Okay. Now, the area, the cross-sectional area, is going to be the area of a square, which is the length of a side squared. So it'll be all of this squared. Okay, so the volume. Okay, so the volume is going to be the integral from 0 to h of this squared dy. Okay, so that's our cross-sectional area. It just comes from this, from c to g of a of y dy. C is 0, and d is h, is the top height. Okay, so 0 to h are that. Okay, so we integrate this. Now this is the only variable. Everything else, a, b, and h, are just constants. Okay, so y is the only variable. So you can think of the integral like this. So this is squared, right? So integral cubed, okay? Now, if we take the derivative of this, we'll have a 3 coming down. So I'm going to put a 3 down here to counter that. So I have a 3 come down. That 3 is ready to meet it and cancel it out. This will reduce to 2. Okay, so we'll have all of this squared. Now, you take the derivative of the inside, which will be the derivative of this piece, which is a minus b over h. So we're going to put an h over a minus b to counter that, plus 0. Okay, so now, let's run through this really carefully. If we take the derivative of this, we have a 3 coming down. The 3 cancels with that 3. So those 3's are gone. This reduces to 2, so we have that. Derivative of the inside is just this piece. A minus b over h comes out. The h, this h is in the denominator. It cancels that h. The a minus b up here cancels with that one. And we just get exactly this. Okay, and now you're integrating from 0 to h. Okay, now you put in, I'm running out of space. Let's do one more line. Okay, so you put in h first. Put an h in first. So you put an H in here. Then you subtract and put a 0 in. So put a 0 in here. That's all going to be 0. Okay, now these H's are going to cancel. When you have A minus B plus B, so those B's are going to cancel. Now this H, so you have, this is basically just A cubed. So the numerator is H times A cubed minus B cubed. And the denominator is 3 times A minus B. Okay, now, let's see, you can factor that. So A cubed minus B cubed is A minus B times A squared plus AB plus B squared. And all right, those guys cancel. Okay, and so then in the end, you have H times A squared plus AB plus B squared all over 3. That's the answer. So that's what's going to go in right here. So this will be H times A squared plus AB plus B squared all over 3. Okay, so that will be the answer to the first part. Okay, now the next part. Okay, so here, what happens if A equals B? Okay, we'll just set A equal to B here. Well, what will happen is instead of this being shorter than this one down here, this will be the same size. So you'll have a rectangular solid. Okay, you'll have a rectangular solid. And when A equals B, you're going to have, okay, so we set A to B squared, we get, okay, it says in terms of B and H. Okay, so we'll replace this A with a B, so that's B squared. Replace this A with a B, that's another B squared, and then this A with this is just B squared. You have 3B squared, so it's divided by 3, so it's HB squared. Okay, which is what you expect it to be. And then the last part is what happens if A equals 0. Okay, so you just what you're going to have there is if A is 0, then you just have, it ends at a point. So we have a square pyramid. Okay, and so when A is 0, you plug a 0 in for A here, you have that's 0, so you just have HB squared over 3.